The topic today is thermodynamics, or the topics of the unit. This is basically the study of heat and how it transfers energy from one place to another. So you can get you can experience thermodynamics very easily just by rubbing your hands together for a few seconds. They will get warm, and that warmth is thermal energy. We sort of quote unquote created heat, although that's kind of a not too politically correct to say that. So thermodynamics is the study of work and heat flow and the energy of a system, the movement of thermal energy, which is known as heat. I was a chemical engineer, and we did a lot with thermodynamics, with chemical processes and things like that. So this is used, it's used all over the place with power plants and cars and all kinds of things. Typically, when we examine the universe, we look at a small part of it, and that little small part that we look at is designated as our system. So it might be an automobile engine, or it could be a turbine in a power plant, or it could be the inside of a microwave, or something along those lines. So some definition. Thermal energy is quote unquote heat energy that's stored in an object. It's basically in the form of the moving atoms or molecules of the substance, as well as energy that was stored or released during phase change, meaning melting or boiling, and things along that nature. Heat is thermal energy that's in transit from one object to another object due to a temperature difference. And temperature is known as the average kinetic energy of the particles in an object, not the total amount of kinetic energy. That would be more related to thermal energy. It's the average kinetic energy. Basically, it's how fast the atoms are moving in a substance. It's a relationship of that. So the difference between temperature and thermal energy. So if I've got these two metal chunks. One is twice the mass of the other, and they're both at 110 degrees Fahrenheit or something along those lines. It would have taken twice as much heat to heat up this bigger block than it would this smaller block. So we say that this block has more thermal energy, even though it's at the same temperature. So that's how a frozen swimming pool can have more thermal energy than a Dixie cup of warm water, because there's a lot more molecules that are in the pool of water. So anyway, so some temperatures to be familiar with. The freezing point of water in Celsius. Celsius is based on water. So 0 is defined as the freezing point of water, and the boiling point is known as 100. Sorry, we had a dog barking attack there. Celsius, water freezes at 0 degrees Celsius and 100 degrees C. It boils. That's the basis of the Celsius system. Water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. And the absolute scale of Celsius is Kelvin, and 0 degrees C is actually 273 Kelvin. And water boils at 373 Kelvin. So when you increase the temperature of an object, the atoms start moving faster, and when you cool an object, the atoms start moving slower. The slowest you can get an object is stopped, and the coldest you can get a substance is absolute 0, which is 0 Kelvin. So that is the Kelvin is based off of absolute 0. Celsius is not. So anyway, so you can convert between these using these formulas. Here's temperature in Kelvin to temperature in Celsius. Now, the absolute scale of Celsius is Kelvin. Fahrenheit has an absolute scale too, that's called Rankine. And so to convert Rankine into or Fahrenheit into Rankine, you add 460 to it. So here's to convert Celsius into Fahrenheit, and here's to convert Fahrenheit into Celsius, where they just solve that equation for you. Here's an example where they go through all that. You can pause this and look at that more if you're interested, but basically they use those formulas. Okay. Thermal equilibrium basically means that two things are at the same temperature. When two substances are at thermal equilibrium, work cannot be done. Now that's ignoring the fact that energy can be stored in the chemical bonds of a substance like gasoline, but ignoring that sort of thing. When two substances reach the same temperature, you lose the energy to do work. There's three laws of thermodynamics. They came up with the first law and then the second law, and they came back and were like, we need one more law, but that was fundamental for the other two, and they called it the 0th law of thermodynamics. And basically what it says is, if A is the same temperature as C and B is the same temperature as C, then A and B are at the same temperature. Okay, so I forget why they needed that, but they did. Okay, so three types of thermal energy transfer, which again is heat, conduction, convection, and radiation. Okay, so the first law of thermodynamics is basically that energy can't be created or destroyed, but it can move from one place to another. You can reword this as saying the energy's got to come from somewhere, and if you lose energy, energy's got to go somewhere. It can't just disappear, and it can't just appear from nowhere. It's got to come from someplace. So, if we're looking at a little part of the universe, we can put energy into that little part of the universe. For example, when I pump gasoline into my car, if my car is my system, I'm increasing the energy of my car. But that energy came from somewhere else. I'm taking the gasoline from the universe. So, example, using a bicycle pump. So when you pump the bicycle pump gets hot. Where did that energy come from? Well, that was the work that I was doing by pushing the handle down. I was doing work, and that's where the energy came from. Okay. The second law of thermodynamics it really has to do with a concept called entropy, and we're not going to get into entropy very deep. But one of the second law of thermodynamics is that things tend to happen that increase the entropy of an object or of a system, or things tend to go from order to disorder is one very, very basic way of looking at it. And one of the consequences of that is basically heat flows from hot things to cold things. High temperature objects tend to lose heat to cold temperature objects. When you have a hot piece of pizza, that thermal energy leaves the pizza and goes to the room because the room is colder. And when you take a bite of that hot piece of pizza and you burn the roof of your mouth, thermal energy was transferred from the pizza to your mouth. The real basic understanding of entropy is that it's the tendency of things to go from order to disorder. It's how evenly this heat energy, how evenly energy is distributed within a system. It's not even really worth going into entropy because there's kind of a lot to it, but basically order to disorder. Okay, so types of thermal energy transfer, aka heat, convection. This basically is the kind of circular patterns that form when you heat up a fluid, either a gas or a liquid. So, for example, if you were to heat the bottom of a beaker of water or a container of water, that hot water would expand, get less dense than the cold water, and then rise to the top. And then the cold water that was at the top would come to the bottom and get heated, and then you get these circular patterns. So basically, it's the transfer energy by movement of a fluid. That's natural convection. You can have what's called forced convection, basically when you use a fan and you blow, a fluid. For example, a hairdryer. is both natural convection and forced convection. Mostly it's forced convection because the fan blows the air across the heating element and blows it to your hair. Conduction is the energy that's transferred between two objects that are in contact. So if you, for example, if you had a hot spoon that was sitting in the soup and you touch that hot spoon to your mouth or to your tongue, energy would conduct from the hot spoon to your mouth, to your tongue. Or if you were to leave it in long enough, the end of the spoon would get warm because the heat would be conducting along the length of the spoon. So conduct, and because the bits of spoon are in contact with other bits of spoon. So anyway, thermal energy. There's radiation. This is energy that's transferred in the form of electromagnetic waves, of which light is one type. Visible light is one type. So you've experienced radiation, and we're not talking about nuclear radiation here. Don't get out your hazmat suit or anything like that. For example, your microwave ovens use a form of light that we cannot see, called microwaves, strangely enough, and basically it's like a big microwave, a flashlight, and it shines these microwaves, and the food picks up the microwave, absorbs them, and gets warm. If you've ever been standing in front of a big roaring campfire and then had somebody walk in front of you and you notice that your skin cooled very quickly, and then as soon as they pass, your skin warms up again very quickly. When the person was between you and the fire, they were blocking the radiation energy that was coming from the fire. Basically, it was blocking infrared light. Infrared light is just a little bit longer than regular red light. We can't see it because our eyes just aren't tuned to it. Although, venomous snakes can see. They have pits which can detect infrared light, which is how they detect their rodent prey and things along that nature. We emit infrared light. We radiate that energy out. That is energy that we're losing to our surroundings because we are radiating like a light bulb, that type of energy. In order to, if somebody is in need of retaining their heat and it's an emergency, they've got these foil. They're very, very thin blankets. They're not going to prevent much conduction. They're not really much of an insulator. But what they do is they're shiny, so they reflect that radiant energy back to you. These are known as emergency blankets. So this is a house, and it's being looked at in infrared light. And we're looking for areas that we're losing heat that we could insulate better. You can see that the windows are red, and it's red up here, and it's red at the very top. That's where we're losing energy the most. For the most part, the walls look pretty decent. Notice this is some insulation, and it's foil backed to reflect that radiation because it is a form of light. You can reflect it back into the house, or during the summertime we reflect it away from the house. These are the equations that you're going to be using in this unit. Q, which is basically equal to heat, or the change in thermal energy. M is mass. C is what's known as the specific heat of a substance, and capital delta T is the change in temperature of a substance. And we'll go through the rest of these equations a little bit later on. But these are the equations. So note they're 9.15 and 9.38 are where they're at. The first equation we're going to use is this one, and basically it's this. Okay, the heat absorbed by a substance depends on how much of it there is, what kind of substance it is, and how much the temperature went up. Okay, so Q is equal to the energy transfer or heat. M is the mass, and now it's important to note that that's in kilograms. C is the specific heat capacity. Not all substances heat up evenly or heat up the same if you pump the same amount of heat into them. For example, water will absorb a lot of heat without increasing in temperature very much. It kind of has a lot of what you might think of as thermal inertia, but really what it's said to have is a high specific heat capacity. And delta T is how much the temperature of that thing changed by. So here's an example. We've got a chunk of aluminum that's initially at 80 degrees. We place it in a liter of water, which is also 1 kilogram of water that's originally at 25 degrees C. After they both come to equilibrium, after the heat stops flowing, they're both at 30 degrees C. Calculate the heat absorbed by the water and the mass of the aluminum block. Okay, so it's given that we've got 1 kilogram of water and the specific heat capacity of water is 4,184, which is a pretty big number because again, water has a pretty high heat capacity. For metals and things like that, it'll be quite a bit smaller than that. So let's look at it. So let's look for the heat that the water absorbs, because we've got enough for that. Okay. So Q equals MC delta T. So solve for the Q of the water. So the mass of the water is 1 kilogram. M is 1 kilogram. C, the C of water was given to us as 4,184. And the delta T, where did that come from? Where did we get 5 degrees C from? Well, if you go back to the original problem, it said that the water was originally at 25 degrees C, and then after you put in the aluminum block, the water is warmed up to 30 degrees C. So it absorbed 5 degrees C. So that's where that temperature, or that's where that came from. And so the water, since it warmed up, it gained about 21,000 joules of energy, of thermal energy. Next, what we want to do is solve for the amount of mass of the aluminum. I don't know why they do this, but they like to have you solve for the mass of one of the substances, whatever. So what we're going to say is basically, however much water or heat the water gained is going to equal to the heat that the aluminum lost. Okay, that makes enough sense. The water got warmer, the aluminum got colder. Okay, the water gained 21,920. The aluminum must have lost it. So we're going to say the heat that the aluminum loses is equal to the mass of the aluminum times the specific heat capacity of the aluminum times the change in temperature of the aluminum. And then here they go ahead and solve this for the mass of the aluminum instead of putting in numbers and then solving later. So the heat of that the aluminum absorbed is the same as the number that we used before. The specific heat capacity of aluminum, it was given. It was 900 joules per kilogram degrees C. And the delta T was 50 degrees C. Where did we get that 50 degrees C from? Well, we know that the aluminum started at 80 degrees C, and then it cooled down to 30 degrees C. So that's where the delta T comes from, that 50. Okay, and this is where the heat capacity for aluminum came from, is 900. Notice that 900 for aluminum is quite a bit smaller than that of water. And what we get is 0.46 kilograms, or roughly 460 grams.